Hi, my name is Muhammad NOUFHAL bin AZRI, and I'm going to present to you guys of our content in our project of mechanic material. Before we begin, let us briefly go through the contents of our presentation. First, we will introduce our project by explaining the background and objective of the study. Next, we will present the model fabrication process, where we will explain the material used and the step involved in constructing our model. After that, we will discuss the model testing section, where we evaluated the performance of our model and recorded the result. We will then move on to the calculation and diagram section. Here we will explain the engineering calculation, the formulas applied, and the diagrams that support our analysis. Finally, we will conclude our presentation by summarizing the key findings and discussing whether our project successfully achieved its objective.
Hi, I'm CHING. I'm going to share the problem background of this project. So before the project, we need to understand the concept of it. In structural engineering, a material resistant to bending depends heavily on its cross-sectional geometry, material properties, and stress distribution. In this project, we are asked to design and build a standardized structural member using a fragile, non-traditional material, which is uncooled spaghetti. This project focuses specifically on an equilateral triangle cross-section, and we need to evaluate how this specific shape distribute compressive and tensile stresses under a localized bending load until complete failure occurs. To fulfill the project requirements, we have established 4 objectives. The first one, we are creating a bar using uncooled spaghetti with a precise of 1.5 cm equilateral triangle profile and a length of 30 cm. Second, we conduct a model test using the water bottle system, and we neglect the weight of the water bottle. Third, we map up the structural response by generating shear force diagrams and bending moment diagrams. The fourth one, we determine the ultimate stress capacity and calculate the allowable normal stress using a safety factor of 1.5.
So, for the material used throughout the project is cardboard, 1.5 liter of empty water bottle, 200 milliliter of empty water bottle, 500 milliliter of empty water bottle, measuring cup, rope, scissors, sellotape, and last but not least, spaghetti.
This is the first sample bar we have done before the final one. Due to the special properties of the spaghetti bar, we decide to use a thin cardboard to shape it into an equilateral triangle.
So right now, we're trying to figure out how to hang the load using the bar while we're finishing the bar model.
Oh, for sure. This time I was really struggling to insert the spaghetti inside the cupboard, which equilateral triangle shape. It's really need to have full concentration.
We use a water bottle, which is a concentrated load. We are going to tie it on one end of the bar. Then, by using this, we are going to add like every 250 milliliter as intervals until the bar breaks.
Danny,
Yes.
what are we going to do next?
So now we are going to test the bar, and we use the water bottle, like we said, until the bar breaks. Hello, my name is Daniel HARRYTH. I'm from Group 3 of Mechanic of Material, and we are going to test the bar.
My name is SUFFIAN ROSLAN. So we want to test the bar until the bar is straight.
Hi, we are from Group 3 and I'm from CHING. We are going to test our bar.
Hi, I'm Bryan and we are Group 3 and we are going to test out the bar today.
Hi, my name is Muhammad NOUFHAL. I'm from Group 3. So next we are going to test our bar.
So this is our first 250 milliliter water added to the.
So now we want to add 250 milliliter. So we add. The bar still stand, guys.
Okay, now we'll add on 250 more milliliters. The bar is still holding on.
This is our flow weight, 250 milliliters.
So this is our next 250 milliliters.
Hello guys, it's me again. I think personally this is the last one, but we are going to add another 250 milliliter. And what do you know? The bar still stands. So this is another 250 milliliter adding to the. Oh my god, it still stands. It is. Okay. So this is another 150 milliliter adding to the load. Three.
Hi, my name is Brian Chang, and I'll present for the moment calculations, the bending and the shear calculations. So first, we can find out that the mass of the load is 0.25 kilograms, and from that we can find the sum of Y forces as well as the reaction forces of RA and RB, which are 1.226 newtons respectively. And then from that, we are able to find the shearing forces and the bending moments in segment 1, which is 1.226 newtons and 0.1839 newton meter respectively. And from that, we're also able to find segment 2, which has negative 1.2265 newtons for its shearing force and 0.1839 newton meter for its moment. And then finally, we can find segment 3, which has negative 1.2265 newton for its shearing force and 0 newton meters for its moments. And on the right, this is what our graphs will look like if we plot them. Okay, so now we move on to 0.5 kilograms, and from that we're able to find the RA and RB, which is 2.4525 newtons, and from that we're able to find the shearing stress of segment 1, which is 2.4525 newtons, and the moment, which is 0.3679 newton meters, and from that we're able to find segment 2, which has a shearing stress of negative 2.4525 newtons and 0.3679 newton meter for the moment, and finally segment 3, which has negative 2.4525 newtons for its shearing stress and 0 newton meter for its moment. On the right, you're able to see what it will look like if we plot it on a graph. Okay, so now we'll move on to 0.75 kilogram load, and from that we can find the new RA, which is 3.679 newtons, and then from there we can find the new shearing stress, which is 3.679 newtons, and the moment at 0.5519 newton meter. That's for segment 1. For segment 2, we can find the shearing stress of negative 3.6785 newton, and the moment as 0.5519 newton meter. And finally, for segment 3, we can find the shearing stress of negative 3.6785 newtons and a 0 newton meter for the moment. On the right, you can see what it will look like if we plot it on a graph. Okay, so now we'll move on to 1 kilogram, and from that we can find the new RA and RB to be 4.905 Newton, which is the same shearing force as segment 1. And from that we're able to find the moment, which is 0.738558 Newton meter. And from that we're able to find segment 2, which is the same moment, but negative 4.905 Newton for its shearing force. And then from that we're able to find segment 3, which has 0 moment and negative 4.905 Newton for its shearing force. And from that we're able to plot a graph.
Okay, so my name is Muhammad SUFFIAN. I want to present the calculation and the diagram, shear force diagram and body moment diagram for mass 1.25 kilogram. So you use the method of section, we cut into 3 sections and we get V1, V2 and V3 equal to 6.1313 Newton. So we draw the shear force diagram and bending moment diagram. So this is for load of 1.5 kilogram. So we use the same method, which is we get the V value and moment value, V1, V2 and V3, and moment 1, moment 2 and moment 3. V1, V2, V3 equal to 7.3575 Newton, and moment 1 equal to 1.1036 Newton meter, M2 equal to 1.1036 Newton meter, and M3 equal to 0 Newton meter. And we also draw the shear force diagram and bending moment diagram. So for the mass equal to 1.75 kilo, we get the value for V1, V2, V3 equal to 8.5838. And for the moment, we get 1.2871. So once again, we draw a shear force diagram and bending moment diagram. And lastly, for the mass equal to 2 kilogram, we got the V1, V2, V3 equal to 9.81 Newton. And for the moment 1, moment 2, moment 3, we get 14715 Newton meter. We use the same method to calculate it, which is we cut into 3 sections. And for the shear force diagram and bending moment diagram, we draw based on the value we get earlier.
Okay, so now we can look at the table for shearing force and bending moment. As you can see, we have cataloged the mass, the weight, the shearing force, and the maximum moment. As you can see from the table, the maximum mass is 2 kilograms, which is 19.62 newtons, which results in a shearing force of 9.81 newtons and a maximum moment of 1.472 Newton meter. Okay, so now we have to find the safety factor and recommended max weight. To find the safety factor, you have to find the maximum tension, which can be found with the centroid and the inertia, which is shown on the left side here. And from that, we're able to find the maximum tension the spaghetti bar is undergoing, which is 6.8 megapascals. And from that, we can apply the safety factor, which is 1.5, to show that the safe tension is 4.653 megapascals. And for that, we can work backwards to find the safe moment, which is 0.981 Newton moment. And from that, we're able to find the weight, which is 13.08 newtons. And from that, we're able to find a maximum mass of 1.33 kilograms.
Hi, my name is Muhammad NOUFHAL bin AZRI, and I'm going to present a conclusion of our group project Mechanic Material. In conclusion, this project successfully bridged theoretical mechanics with practical engineering through the destructive testing of an equilateral triangle spaghetti bar. The physical execution demonstrated how cross-sectional geometry dictates a member's resistance to bending and ultimate load capacity. Mathematically, converting fluid volume to force, plotting shear force and bending moment diagrams, and applying the flexure formula reinforced the role of static equilibrium in predicting structural failure. Factoring in a 1.5 safety factor provided a real-world perspective on how engineers establish safe operational threshold to prevent collapse. Ultimately, the project highlighted how manufacturing quality directly impacts real-world strength while emphasizing the value of structured teamwork in executing an engineering analysis from fabrication to final calculation. That's all from me.